Hello and good evening, friends. So today we're going to actually start the mathematics, and so this is the second chapter. So chapter 2 of mathematics for machine learning book, and then that's linear algebra. So that's chapter 2. So we're going to start, and as usual, we'll start reading a little bit and then talk as I go along. And then, like explained in the first chapter, they are again talking about a little bit about when formalizing intuitive concepts, a common approach is to construct a set of objects. So you construct a set of objects and they are also calling it symbols, and a set of rules to manipulate means like operate on them, right? Manipulate these objects, let's say manipulate them, right? So we have a set of objects or symbols and then a set of rules to manipulate them, right? These two together in mathematics is known as an algebra, right? So we are familiar with numbers, just like natural numbers, right? Counting numbers, and we have rules like addition, multiplication, and so on, right? So that's like an algebra, right? Now linear algebra is the study of vectors and certain rules to manipulate vectors. So linear algebra is all about vectors, right? So it's about vectors. So vectors are the objects and then what rules apply to them for manipulation, right? So the vectors many of us know from school are called the geometric vectors, right? So the geometric vectors are what we learnt in school, where you will remember this x and then we put an arrow above, or a y and then an arrow above it, and then typically if you think about these in school level mathematics, we would have done things like, for example, x 1 2 3 and so on, y 1 2 3, and then to denote a vector like 1 comma 3, so we would take this point and then this becomes the vector 1 comma 3, right? So this is kind of the school level, and then we usually used to denote like this. This is how in physics also things are done, right? But then when it comes to mathematics, it's a little bit more general than this. So more general concepts of vector, and then as we discussed in the notation, we are going to use this symbol, right? So x, and then in the book it will be bolded, lowercase, right? And then when we write in pen, we just put an underline below this, right? So x, y, sometimes even if like some parameter vector, we'll write theta and then put an underscore below to denote that it's actually a vector, right? So in general, vectors are special objects that can be added together. So what are manipulations, right? So here they are talking about manipulation. So what can we do to vectors? So we can add them, right? So add two vectors, and then you can multiply a vector by a scalar. So that's called a scalar multiplication, right? So you can add two vectors and then you can multiply a vector by a scalar. That's called scalar multiplication. From an abstract mathematical viewpoint, any object that satisfies these two properties can be considered a vector. Here are some examples of such vector objects. So the geometric vectors like these ones are also of this nature, right, which we can also write in this more general form, right? So they are directed and they can be drawn, and geometric vectors can be added, right? This is from our school. So for example, let's say this is x, and then I want to say this is y, right? Y is in this case 3 comma 1, right? So I'm drawing another guy like here, and this is vector y. Okay, so that's vector y. So let me write this. So this x is 1 comma 3 and y is 3 comma 1, right? And we can add them, right? And we have done this in school. So generally what we do is you travel along one vector first, right? So for example, let's say I travel along x, so I reach the point 1 3, and then from there I basically take this y vector and then move it, right? So that's going to give me that's going to be 4, and then it's 1 up, so it's going to be 4 here also, right? So it's going to be going there, right? And then that is going to be the sum z, right? Z vector, if you want to call it z or z equal to x plus y, right? And that's 4 4, and that's what we've drawn here, right? So you, or the same thing can be also obtained by moving along y and then from there applying x, right? So that's fine as well, right? So it reaches to the same point, right? Actually this is incorrect, this is not z, this is just y. The z vector is this guy, this is z, sorry about that, right? So this is the sum of x and y. These are the geometric vectors, right? So that's the first class that they are saying. Some examples, right? So geometric, so that's the first one, right? And then we can also do scalar multiplication, which is for geometric, right? So this is, so we can do this x plus y equal to z, and then we can also do some lambda times x, where lambda is some real number, right? So for example, 3x, right? In this case 3x is going to be with this x that I'm taking 1 comma 3 is going to be 3 comma 9, right? And then that will be 3 times as long as this one, and then negative 3x is just going to be pointing to the other direction, right? So negatives from, so negative 3x is minus 3 minus 9 or 4x or whatever it is, but it's going to be, it's pointing in the other direction, okay? I'm not drawing it here, but I hope that that's clear. In fact, it is the original vector scaled by this one. They're talking about scaled by lambda. So geometric vectors are instances of the vector concepts introduced previously. Interpreting vectors as geometric vectors enables us to use our intuitions about direction and magnitude to reason about mathematical operations. Okay, so that's the first example. The second, a little bit more interesting example is what are known as polynomials, right? So now if you look at polynomials, so two polynomials can be added, right? And then polynomials, right? So for example, any two polynomials, you know that you can add two polynomials. So if I for example, so just let's take an example where I have x square minus 2x plus 4. So one polynomial, another one is x cube minus 1. So these two are polynomials, and obviously we can add them, and then the sum, if I call this for example f of x, if we want to call it f of x, or we can also think of them as vectors, right, which is what this whole point is, right? And then we can add them up, in which case the third degree x cube is just 1, so that's going to be there once, and then this x square is going to come from this polynomial, from then there is no x term, so it's going to be minus 2x, but then the constant we are going to have plus 3, right? So this is allowed, so addition is fine, right? So this is addition, and then of course scalar multiplication, you just take a scalar and multiply them, right? So as long as those operations are allowed, they are considered vectors, right? Now they are rather unusual, right? And then polynomials are very different from geometric vectors, right? So geometric vectors are like you can draw them, polynomials are more abstract, right? And they are both vectors in this kind of mathematical sense, that we are trying to use. So third one, the example that is given is audio signals. What does that mean? So why is an audio signal a vector? So you generally audio signals are represented by numbers in what is known as a time series, right? So it's known as a time series, right? As I'm talking, my voice is being converted internally by various devices in the microphone, and then eventually it becomes digitized, and then it becomes series of numbers, right? And then we can add two audio signals together, and then we can multiply it by a scalar, right, which will increase the volume and so on, right? So all of them, as long as you take two audio signals and you can add them, and you can take a single audio signal and multiply it by some constant number, it's good, right? And then the last one is more abstract than anything else, is basically this space Rn, right? So Rn is basically this n dimensional or n tuples of real numbers, right? Tuple meaning it's an ordered set of n numbers, right? It is more abstract than polynomials, and it is the concept we focus on in this book. And then, like we saw before, if you take a vector like this, right? So 1 2, and this belongs to R2, okay, and so on. So adding two vectors, let's see what that does. So you have A, so let me put this underline. So it's a vector A comma B, if they belong to Rn, right? Then how do you add two vectors? You just add the components, right? They have to be of same dimension, obviously, because only then you can add the vectors, and then you can add them by just adding the component wise elements, right? So A plus B is going to give some other vector C, right, which is also in the same Rn, right? And then some lambda times A, right, with lambda being a real number, right? It's scalar multiplication, which means this lambda is not a vector, right? So it's just a real number. Lambda times A, that also again is going to be Rn, right? So for example, in this case, if I take 1 by 3 times A, that's nothing but going to be the vector 1 by 3, 2 by 3, right? So this is also again an element of R2, right? So that's basically the idea behind this Rn, right? And many programming languages support array operations, which allow for convenient implementation of algorithms that involve vector operations. That's if you go to Python. Python has built-in data type called tuple that can be used for this purpose, or that's basically a fixed length. If they are called immutable in Python, and then you also have lists, but in machine learning we don't use the Python built-in types. There is this whole library called NumPy, 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 and then it's usually imported as a module, and then this is what is used in Python for doing all these kind of array operations, right? It's very efficient, and it executes in parallel on the computer, so it can do things very efficiently and much faster, and then very useful for machine learning and deep learning and all the ML algorithms. Okay, so let's move on, and linear algebra focuses on the similarities between these vector concepts. We can add them together and multiply them by scalars. We'll largely focus on vectors in Rn, since most algorithms in linear algebra are formulated in Rn. Right? We'll see in chapter 8 that we often consider data to be represented as vectors in Rn. In this book, we will focus on finite dimensional vector spaces, in which case there is a one-to-one correspondence between any kind of vector and Rn. When it is convenient, we will use intuitions about geometric vectors and consider array-based algorithms. And then One major idea in mathematics is the idea of closure. So let's talk about closure. What is a closure? Right, closure, closure. And this is the question, right? So what is the set of all things that can result from my proposed operations? In the case of vectors, what is the set of vectors that can result by starting with a small set of vectors and adding them to each other and scaling them, right? So this results in, okay, what is a closure? So I'm going to go to this, I'm going to take a simple example, right? So I'm going to consider this R2, okay, right? So R2, I'm not going to consider initially all of R2, okay? I'm just going to take only two vectors from R2, right? So I'm going to take, for example, 1, 0 and then 0, 1, right? So these are the two vectors, they are called the unit vectors, right? I take only this set initially, right? Not all of R2, right? Which means not every element belonging to R2. So we are going to, you remember, like we just told that an algebra is basically a set of objects and then some rules to manipulate them. We know the rules now for linear algebra, which is you should be able to add any two vectors and then you should be able to multiply a vector by a scalar, right? And then if we look at closure, if you do those operations, for example, if I add these two up simply, then I get, so I'm going to call this as E1, if you remember from our previous notation, this is E1 in R2 and this is E2 in R2, okay. Now if I add E1 plus E2, then I get 1, 1, right? And then I can always scale E1 by any number I want, right? So if I, for example, I scale E1 by lambda 1, right? Lambda 1 E1 is going to give me just lambda 1 0, right? And then of course this lambda 1 belongs to R, right? That's scalar multiplication. And then if I take lambda 2 E2, this is going to be equal to 0 lambda 2, right? And then lambda 2 again belongs to R. And then if I add these two up, lambda 1 E1, because again these are two vectors and I'm just looking for all possible vectors that I can obtain by just doing addition and scalar multiplication and addition again of those resulting vectors and then seeing what all we can get, right? So if I say lambda 1 E1 plus lambda 2 E2, that's going to be lambda 1 lambda 2, where lambda 1 lambda 2 belongs to real numbers, right? Now if you see this, what this is, this definition, right, that essentially you can get all the vectors in R2 from these two, just these two vectors, right? Why is that the case? Because lambda 1 lambda 2 can be any real numbers, right? It can be any real, lambda 1 can be any real number, lambda 2 can be any real number. That means it's just basically a two-dimensional vector, each one being a real number, which means it's the whole of R2. So the closure of what this is, later on we'll see, this is a what is known as a basis, right, for this vector space. So this whole thing, right, this whole space of vectors that are resulting from this addition and scalar multiplication, this is called a vector space, right? So R2 is a vector space, right? Now we will cover vector space later on, right? The concept of a vector space and its properties underlie much of machine learning, and then they are giving a figure in which they are summarizing the concepts that I don't think that we need right now. So we'll just move on, right? And then they are giving some references for some books of where they have taken their materials from, and we don't need it right now. I myself referred at some point Gilbert Strang's linear algebra course in MIT OpenCourseware, so that might be useful, but we don't need that because that's basically what we are doing here ourselves from this book. And then there is also linear algebra series by 3 Blue 1 Brown, which I think is a YouTube channel. I've heard good reviews of that as well. Okay. And then let's see what what the authors are saying. Linear algebra plays an important role in machine learning and general mathematics. The concepts introduced in this chapter are further expanded to include the idea of geometry in chapter 3. So that's going to be analytic geometry. Then in chapter 5, we'll discuss vector calculus, where a principled knowledge of matrix operations is essential. Okay, so whatever matrices are, we'll come to that and we'll learn about that. And then in chapter 10, which is an application chapter in part 2, right? It's actually in machine learning algorithm, right? We will use projections for dimensionality reduction with principal components analysis. And in chapter 9, we'll discuss linear regression. Linear algebra again plays a central role for solving what are known as least squares problems. Okay, so that's a little bit of motivation as to what's going on. Why are we doing all this? That kind of, it answers that question. Okay, so now we'll look at some of this, actually this next section, which is on systems of linear equations. So that's 2.1, that's systems of linear equations. So what is this? We remember what generally called simultaneous equations in school level algebra. It just generalized, right? So the systems of linear equations play a central part in linear algebra. Many problems can be formulated as systems of linear equations, and linear algebra gives us the tools for solving them. Okay, so now they're taking an example here of a company that produces products. So these are products, and the products are called uppercase N1, N2, all the way up to N, uppercase N subscript lowercase n. So there are lowercase n number of products, and then for them they are made with resources, right? So the resources are R1 and R2 up to Rm resources, and then to produce, so to produce a unit of product Nj, right? So they are using this notation, A I j units of R I are needed, right? So what does this mean? So this means, okay, so these are indices, right? So let's say there are 3 products and 2 resources, right? And then for one of the products, how many units of each resource is required. So that's what this is in a little bit generalized in a symbolic notation, right? The objective is to find an optimal production plan, that is a plan of how many units xj of product nj should be produced if a total of bi units of resource ri are available, and ideally no resources are left over, right? So they are saying that bi units of resource ri, so available units of ri, right? So this is bi, right? So the bi means, let's say for example you're making pastries, right? And then you need flour, and then you need sugar, right? And then you have some milk and whatever else is required to make different kinds of pastries, right? So these are you can make multiple pastries with the same ingredients. Okay, now the available units of all these resources, that's like, for example, let's say you have 10 kilograms of flour, then that's bi, right? Bi is 10 for that resource ri. Okay, and what we want to make sure that we use all these ingredients, right? And then make as many products are as required, right? Now, so the units of product Nj, okay, so number or let's say units of Nj produced, right, produced is denoted by Xj, right, which means let's say we are making one kind of, like this is, let's say pastry 1, I'm just going to call it pastry 1. So how many units of that pastry is produced, that's Xj, and remember this Bi is the unit of the resource, right? So that's that. Now if we produce, so basically we will produce x1 units of n1, x2 units of n2, and x subscript lowercase n units of this uppercase n this product, right? So we want to know for these products what are the, for making all these n products, how many units of Ri are required. So the question that's being asked is how many units of Ri needed, right? So this is the question we are asking. Now we want to write an expression for this, okay? How many units of the resource Ri are needed, right, for the overall production of all the pastries, okay? So if I come back here, I know the I is fixed, so that's going to be Ai, right? So this I is fixed in this case, the Aij here, and then I'm going to go and add them up all for all these n products, right? So that's going to be Ai, for the first one this is 1, Ai1 times I'm making x1 units of this n1, right? So I'm going to have x1, right? And then for the next one again the resource is again I, so Ai2 times x2, right, and so on up to Ai, and the last one is this lowercase n and xn, right? So this is how many units of Ri are needed overall, right, for making all these products, right? An optimal production plan. So okay, so now we come to this optimal production plan, right? So what is this plan? This plan has to satisfy the following system of equations. So this has to satisfy, so let's take the resource R1. We know that we have how many units of R1 available, B1 units of R1 are available. So if we take this whole thing for the I equal to 1 case, it has to be equal to B1, right? So we need A11 x1 plus A12 x2 up to A1n xn should be equal to B1, right? And then the second one and so on. Like this, how many equations we have, right? So we are going to have m as Mary, right? A m1 x1 plus a m2 x2 etc. up to a m n xn, right, equal to b m as Mary, right? So there are m resources, so we have written one equation for each resource, right? So it has to satisfy all these, right? Then we have an optimal production plan because we've used all the available ingredients, that is the B1 units of R1, B2 units of R2 and so on up to BM units of RM. They are all used for making these products, right? So that's what this whole equation is talking about, right? Now this is the motivation for the matrix notation as well as column vector notation and so on, which we'll see in a moment, right? But we'll take some other example, right? So this is called as the system of linear equations, right? So this whole this set of equations, right? So this set of equations, this is the system of linear equations. Okay, so that's that. And then the x I, these are the unknowns, right? And then so every every n tuple, so now they are saying n tuple, right, which is n tuple is same as an r dimensional, sorry, n dimensional vector, right? So xn, which belongs to this, right, Rn. So anything that satisfies this equation is called a solution, right? So those are the solutions of that system of linear equations. Okay. So this notation might be a little bit, if you're not familiar with this kind of symbolic math, this is usually daunting, but when we do some examples, this will become clear. So we'll stop here for this lecture, and then we'll continue from the next lecture on this.